In this video, we're going to talk about rational functions and when they have vertical asymptotes, holes, horizontal asymptotes, and oblique asymptotes. So right now we can see the very simple 1 over x, and it has a vertical asymptote of x equals 0. And notice how if I change the linear function in the denominator here, it changes where the vertical asymptote is. Now the vertical asymptote is at x is equal to 1 because I transformed it 1 to the right. I can make it 2 to the right, 3 to the right, okay? But notice that the vertical asymptote occurs at a value that would make us divide by 0. We're never allowed to divide by 0. 1 divided by 0 does not exist. So I can add another factor into the denominator and make it a quadratic. And now there's 2 vertical asymptotes. 1 for each value in the denominator, that would make it 0. Those are the values that do not exist in the domain of this function. Okay? Now what if I have something in the top? It didn't really make too big of a difference. We still have those vertical asymptotes here. And then notice how it added something new in here. It crosses. It just happens to cross because if we sub in a value of 2, it's going to make the numerator equal to 0. 2 minus 2 is 0. And then 0 divided by anything is still equal to 0. So it's an x-intercept because x value of 0, x value of 2 y value of 0. Okay? But notice, if I make it so it has the exact same factor as the denominator, now it looks a lot like the plain old 1 over x minus 3. See how these look the exact same? They're not exactly the same. In the f at x function, if we try to sub in a value of 1, it's undefined because we would have 0 divided by 0, and we can never ever divide by 0 in mathematics. But for the g at x, it doesn't matter if I put in 1 because it doesn't have that factor of x minus 1. So although these functions look like they're the exact same, x minus 1 is actually a whole. So I should draw a whole at x is equal to 1 on the function. So that should be a whole. So when we do a whole, empty in the middle, circle, it means it's not in the domain. So anytime you have a factor in the top and the bottom, it means that there's a whole. Okay? And if you're doing some algebra and you want to simplify and you want to cross these out, the only way you're allowed to cross those out is if you make a point of saying x cannot equal positive, not negative. Could I erase that? X cannot equal positive 1. Okay? Because otherwise, if we were to cancel that out, it really ends up looking just like g at x. But we see that g at x is not the exact same because it doesn't have a whole. So earlier when I was drawing that whole, I should have been looking at my f at x really because g at x doesn't have a whole. Okay? So it's really important. So anytime you're given these equations that have a polynomial on the top and the polynomial on the bottom and you want to graph it, try factoring everything. If there's a common factor in the top and the bottom, you know it's a whole. And if you're looking for the solution to a function, then it wouldn't be a solution because it's not in the domain of the function. Alright, so what's next? I'm going to try to erase that off the screen. And the next thing that we're going to talk about is horizontal asymptotes. So we just talked about holes and vertical asymptotes, and those are discontinuities because they're places where the domain doesn't exist. They're breaks in the function. Okay? Now we're going to talk about horizontal asymptotes. So notice in the function that we have right now, let's look at the g at x one. What's the horizontal? What's the horizontal asymptote? I missed erasing one little thing. Okay. So the horizontal asymptote, what is the value as, what's the end behavior is basically what you're asking. As the x values get very, very, very big, or in the negative infinity direction, very, very, very little, what happens to the function? Well, you can see it. It's going to 0. And if we sub it in, so we put in 100, we can see that it's going to 0. I can put in 1,000. Okay? So we can see that it's going to 0. And I can add another function in the denominator here. And we can see that it's still going to 0. It actually went to 0 a little more quickly. Doesn't really matter. We're really looking at where it does eventually go to. So the horizontal asymptote is still y is equal to 0. And I could put any quadratic in the bottom. I could even put a cubic, and still it goes to 0. Because the denominator is going to get very, very big as we put in big values. If we sub in 10 for each of these x's, let's say 100, we sub in 100, then we'll have 100 minus 3 times 100 minus 1 times 100 plus 1. That's going to be very close to 100 times 100 times 100. A really big number. 1 divided by a really big number, very small number, so it's going to 0. Something different happens when we have the same degree on the top and the bottom. So I'm just picking any factors. I'm not really thinking these through. So when we have a quadratic in the top and a quadratic in the bottom, different things happen. Let's see if we can see this a little bit better. It's hard to see off the graph what the horizontal asymptote is, but it's clear that it's not 0. So let's see, let's sub in a really big value. So far it's looking like it might be 2. Oh, now it looks like it might be 1. What do you think? I think the horizontal asymptote is y is equal to 1. Okay? What if there's a coefficient? Now we have a horizontal asymptote of 2. Why? Because as x gets very, very big, all of the factors become very large numbers. So the top is a big number times 2, and the bottom is a big number. The big numbers kind of cancel each other out, and we're left with 2. Similarly, we could make it a fraction. 2 over 5 is about 0.4. So in general, when the degree of the top and the degree of the bottom is the same, then the horizontal asymptote is the ratio of the coefficients of the numerator and the denominator. So again, we can do 5 over 2, which is 2.5, and you can see that that's happening. So we saw a case where the degree of, right now we're seeing the degree of the numerator is equal to the degree of the denominator. We talked about the degree of the denominator is bigger than the degree of the numerator. What's the only case left that we haven't looked at? Well, what if the numerator is bigger than the denominator? Kind of looks like a line with a little blip in between, doesn't it? This is called an oblique asymptote. Because in general, say I have an equation like this, it's a line. The x plus 1 and the x plus 1 in the numerator and the x plus 1 in the denominator canceled each other out, right? So even if I change this number a little bit, so now we have a vertical asymptote because we can't sub in 1 in the denominator. So it swings up for the vertical asymptote, but over time, the x's kind of cancel each other out, and the linear term takes over time. And it eventually has more of a linear behavior. So the oblique asymptote, it's not a horizontal asymptote, it goes off in like a linear function that's not horizontal. Okay? And an oblique asymptote happens when the degree of the denominator is bigger than the degree of the numerator, is bigger than the degree of the denominator. But let's see what happens when the degree is much larger. So let's add another factor. 1 minus 2. Let's add another factor. Oh, is this an oblique asymptote? No. So the oblique asymptote only happens in one situation. That's what we saw before. When the degree of the numerator is exactly 1 more than the degree of the denominator. So say I do some more terms. I'm trying to make it so nothing cancels. Okay, so in this situation there's a lot happening right in the middle around those vertical asymptotes, but then over time, again we have an oblique asymptote. And notice that the degree of the numerator was 3 and the degree of the denominator was 2. So because the degree of the numerator was exactly 1 more than the degree of the denominator, we have an oblique asymptote. Okay, so the three main things that we talked about in this video were the fact that 1 over x will have a vertical, let me try to zoom in here, we'll have a vertical asymptote anywhere that makes the denominator 0. We can't divide by 0. Okay? And we can turn it into a quadratic, a cubic, whatever. We just can't divide by 0. That's going to be a discontinuity. And if it has the same factor in the top and the bottom, then that's actually a whole. It doesn't exist. Let's see if this will cooperate. At 1. Undefined. It doesn't exist. It's not in the domain. Desmos doesn't show a whole. If you make a graph, I expect you to show a whole. Okay, horizontal asymptote, when the degree of the denominator is bigger than the degree of the numerator, the horizontal asymptote is y equals 0, because that bottom takes over. And when the degree of the numerator and the denominator are equal, then the horizontal asymptote is the coefficients of the numerator and the denominator. Okay, so those were the key topics that we talked about in this video about the discontinuities and horizontal asymptotes of rational functions.